Picture this. It is 1492. You are standing on the deck of a wooden ship somewhere in the middle of the Atlantic Ocean. There is no coastline visible in any direction, no GPS, no printed ocean chart worth trusting, and you are responsible for finding a continent that most Europeans have never seen. Columbus did not guess his way across. He had a system, a repeatable, documented engineering grade system. And by the end of this video, you will understand exactly how it worked. Here's the thing people get wrong about pre-map navigation. They imagine it as wandering, hoping, and occasionally getting lucky. That is not what happened. By the time Columbus sailed, navigators across multiple cultures had been refining their methods for thousands of years. The Minoans of Crete were using celestial navigation in the 2nd millennium BCE. Polynesian sailors were crossing thousands of miles of open Pacific long before Europe had a reliable magnetic compass. This knowledge was not primitive, it was just built differently than what we are used to. The foundation of pre-modern navigation at sea was a technique called dead reckoning. The name sounds grim, but the concept is clean. You know where you started, you track your compass heading, you estimate your speed, and you measure your time. You multiply those three things together and you get a vector. Plot that vector from your last known position and you have your best estimate of where you are now. Then you use that new position as your starting point for the next leg. It is not perfect, but it is structured, repeatable engineering, not guesswork. Speed measurement deserves its own moment because the solution these sailors built is elegant and the modern world still uses it. You take a small sea anchor, tie it to a line, and tie knots in that line at regular intervals. You throw it off the stern, you flip a sand glass, you count how many knots pay out before the glass runs. That count is your speed, nautical miles per hour. The word knot is not a metaphor or a historical accident. It is a literal description of a rope with knots in it streamed off the back of a ship. The unit survived because the method worked. Now here is where it gets precise. Dead reckoning tells you roughly where you are, but errors accumulate over days at sea. The correction came from the sky. In the northern hemisphere, the angle between Polaris and the horizon equals your latitude almost exactly. 1 degree of altitude equals 1 degree of latitude, which equals about 60 nautical miles. Navigators used instruments called quadrants and astrolabes to measure that angle. By the late 1400s, this was routine. Columbus's own logs record regular latitude checks using the sun and stars to anchor his dead reckoning calculations. The toolkit that John Cabot carried on his 1497 voyage to Newfoundland is worth stopping on because it is so concrete. 5 tools plus the sky. A magnetic compass for heading. A log and line for speed. A lead line for depth. A quadrant or astrolabe for latitude. An hourglass for time. That is it. With those 5 instruments and a working knowledge of dead reckoning, he crossed the North Atlantic and made landfall on a continent. Before we write it off as primitive, let us look at what actually survived. The man found Newfoundland. The lead line is one of the most underrated tools in this whole story. It is a lead weight on a rope marked at 1 fathom intervals, where 1 fathom equals 6 feet. You throw it over the side and count the marks as it pays out to get your depth. But here is the clever part. The bottom of the weight was hollowed out and packed with tallow, a waxy animal fat. When it hit the seabed and came back up, it brought a sample with it. Specific harbors had specific bottom signatures recorded in pilot books. 20 fathoms of fine sand with black specks meant you were approaching a known channel. They did not have sonar. They had mud on a rope. The waters off Newfoundland and the Grand Banks were some of the most fished in the world by the early 1500s, and mariners navigating those fog-heavy approaches relied heavily on exactly this technique. The bottom of the Grand Banks has a distinctive texture. Specific mixes of sand, shell, and mud corresponded to known fishing grounds and safe channels described in pilot books that circulated among fishing fleets. These books were essentially tactile maps of the seabed. When visibility dropped to zero in North Atlantic fog, a lead line reading could tell an experienced skipper more than his eyes could. There's another tool worth knowing about called the backstaff. Invented in the 1590s by John Davis. The problem with earlier sun-sighting instruments was that you had to stare directly at the sun to use them, which was uncomfortable and imprecise. Davis's solution was to turn his back to the sun and use the shadow it cast to measure its altitude. You aligned the shadow with the horizon line and read the angle. Cleaner readings, safer on the eyes, and more accurate latitude fixes. A simple design change that improved a critical measurement. That is the kind of engineering refinement that gets lost when people dismiss this era as pre-scientific. Now we need to talk about the technique called sailing the latitude because it is one of the most practical and underappreciated navigation strategies in this whole era. Latitude you could measure with reasonable accuracy. Longitude you could not reliably, not until marine chronometers arrived in the 18th century. So navigators worked around the problem. You sail north or south until your measured latitude matches your destination's latitude. Then you turn and run east or west along that line until land appears. It is not elegant, but it is systematic, and it worked across entire ocean crossings when the alternative was pure guesswork. The Polynesian navigation system is where this story gets genuinely astonishing. These navigators were finding islands only a few tens of kilometers across in the middle of the open Pacific with no magnetic compass, no paper chart, and no metal instruments of any kind. They were doing it reliably enough to settle islands scattered across a triangle roughly the size of North America. The system they built was not mystical. It was systematic, highly structured, and passed down through strict apprenticeship training. They solved this centuries ago. The question is why we forgot. The Polynesian star compass is the core of the system. Navigators memorized the rising and setting bearings of dozens of specific stars as they moved across the sky through the night. Each star rose at a known point on the horizon and set at a known point. That gave you a mental compass rose with far more reference points than a magnetic needle. You steered by keeping a specific star rising at a specific point on the canoe's bow or beam. As that star climbed too high to be useful, you handed off to the next one in the sequence. The knowledge was encoded in chants, stories, and songs that served as navigational memory storage. But stars only work at night in clear weather. Polynesian navigators had another layer to the system that is arguably more impressive: reading ocean swells. Long-period ocean swells travel thousands of miles from their source and pass through island chains, reflecting and refracting as they go. The interference patterns they create are distinctive and predictable. A navigator lying in the hull of the canoe could feel the motion of crossing swells and interpret that motion as directional information. An island below the horizon was detectable by how it disturbed the swell pattern around it. They were reading the ocean the way a surveyor reads a landscape. The Marshall Islands stick charts are one of the most striking artifacts from this tradition, and they are frequently misunderstood. They look like abstract art, a frame of bent sticks with shells attached at intervals, but they are not maps in the Western sense. They do not show islands from above. They show wave and swell patterns, the curved sticks representing the way swells bend and reflect around island groups. The shells mark island positions relative to those patterns. And here is the detail that changes how you understand them. Navigators studied these charts on land as memory training tools. They did not carry them on voyages. The knowledge had to be inside the navigator, not on a piece of paper. The 1970s Hokulea voyages brought all of this back into documented focus. Hawaiian navigators sailed a traditional double-hulled canoe from Hawaii to Tahiti and back using non-instrument navigation. No compass, no sextant, no GPS. The voyage covered roughly 2,500 miles each way. It was not a stunt. It was a careful, documented experiment designed to prove that traditional Pacific wayfinding was a functional, repeatable system and not a romantic legend. It worked. Modern ethnographers and navigation researchers have since documented the underlying star compasses, swell reading techniques, and apprenticeship structures in detail. This is not fringe theory. This is documented engineering. Land navigation, before printed maps, followed its own parallel logic. Armies, traders, and migrants moved by what you might call handrail navigation. You follow a river upstream until it forks. Take the left fork to the ridge, follow the ridge to the distinctive double-peaked hill, then descend to the valley where the old Roman road picks up again. Ridgelines, river systems, game trails, and recognizable formations served as a network of waypoints that did not require paper. Many armies as late as the 18th century still relied heavily on local guides, road networks, and rivers rather than gridded topographic maps because systematic land surveys simply did not cover most of the interior of most continents. The redundancy principle is the thread that runs through every one of these systems, and it is the most transferable lesson for anyone thinking about navigation without electronics today. Historical navigators almost never trusted a single cue. Columbus cross-checked his dead reckoning with celestial latitude fixes and with depth soundings as he approached land. Polynesian navigators layered stars, swells, birds, cloud formations, and watercolor changes. The European coastal sailor combined compass heading, lead line depth, landmark recognition, and tidal timing. The system was always multiple overlapping inputs, not a single source of truth. One device failing did not sink the voyage. What this whole history keeps pointing back to is a simple, uncomfortable fact. The knowledge that let human beings cross oceans and find islands the size of a small county in the middle of the Pacific did not disappear because something better replaced all of it. It disappeared because the people who held it stopped passing it on, and because the institutions that replaced them did not bother to write it down carefully. Polynesian navigation was nearly lost by the early 20th century, not because it stopped working, but because Western shipping and education systems displaced the apprenticeship structures that transmitted it. History did not lose this knowledge by accident. If you have made it this far, you already know the takeaway is not just historical trivia. GPS fails. Devices run out of power. Jamming is a real documented vulnerability in modern navigation systems. The principles that worked for Columbus, for Cabot, for Polynesian navigators finding a speck of land in 10 million square miles of ocean, those principles are not obsolete. Polaris still marks north. The noon sun still marks south in the northern hemisphere. Rivers still run downhill to coasts. Ridgelines still give you orientation. The old ways worked for a reason. If this kind of practical historical knowledge is what you are here for, subscribe and stay close. There's a lot more where this came from.